So, welcome back. Now, we will look into urban heat island, right. Now, to understand that, first we must understand a little bit of radiation concepts, which some of you might be familiar, some you may not be. So, radiation heat flux is written in this manner, that is the heat exchange between two surfaces per unit area. This will be in terms of watt per meter square, is given by equivalent emissivity of the two surfaces. For example, if I have two surfaces, supposing I have two surfaces, one like this, another like that. So, radiation heat exchange between these two surfaces is governed by equivalent emissivity of the two surfaces. Now, what is equivalent emissivity? Every surface has got, it can absorb heat, and once heated up it will radiate, right. Every body have this, if you supply energy to it, it will absorb and it will radiate if it is at higher temperature. So, heat transfer from higher temperature to lower temperature takes by radiation, which does not require any medium, Now, a perfect black body is one, a perfect black body is one, which absorbs, black body absorbs everything, all radiation, right. So, whatever energy comes, it radiates. Then when it emits, it will also emit all radiation, absorbs or emits all radiation. So, but other bodies, other surfaces, they absorb some. Therefore, emissivity is a unitless, dimensionless term, which is basically epsilon is dimensionless term. The emission at a given wavelength by the body under consideration, that divided by that of black body, perfect black body. So, this is a fraction dimensionless. Now, when we talk of two surfaces, one surface, surface 1, surface 2, this has got epsilon 1, let us say this is epsilon 2. So, 1 by epsilon, the equivalent emissivity is given as 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Emissivity of, equivalent emissivity of these two surfaces are given by this equation, right. So, radiation heat flux is governed by equivalent emissivity of the surfaces. This is Stefan-Boltzmann constant, because this is Stefan-Boltzmann law, and this is called configuration factor. The surfaces as they see each other. For example, if I have surface like this, it's a surface, one surface like this, and there is another surface something like this, and they see each other fully, then this value will be 1 face to face, and same area. So, it is 1, but if it is inclined, then projection of 1 will be there on other. So, f value will be less, f value will be different. F value is the what we call configuration factor, or it what one surface is the portion of what it sees, or projection of one surface onto the other, and this is the temperature of the hot body in Kelvin, and this is the temperature of the cold body in Kelvin. So, that is the radiation heat exchange, right. That is the radiation heat exchange. I am not sure whether I told you this earlier. So, Stefan-Boltzmann law is like this: epsilon is equivalent emissivity, sigma is Stefan-Boltzmann constant, and thus 5.7 into 10 to the power minus 8 watt per meter square, and Kelvin minus 4, and this is called configuration factor, right. So, Kirchhoff's law relevant to radiation concepts is absorptivity and emissivity at a lambda is same. Now, if we denote this as the absorptivity and this is the emissivity, because whatever it absorbs at same wavelength it will emit as well, right. A perfect black body does that, and we are talking in terms of emissivity as the ratio of the energy emitted at a given wavelength by the body under consideration, that divided by that of the perfect black body. So, this is what it is, right. So, if you look at, consider sun as a perfect black body and earth as a perfect black body at different temperatures, at their temperature, earth at their temperature. So, you find sun is at 5778 Kelvin, the wavelength it radiates belongs somewhere to this, these are in microns. So, 0.1 to this, so this is a spectrum, and this is of the earth, because the quality of radiation or the wavelength of the radiation is a function of temperature at which the body radiates, right. For example, you can understand this very easily. You take iron and heat it up to that temperature when it becomes red hot, and further heating it will be white. That means, it is radiating wider spectrum of wavelength when it becomes white. If you cool it, it is red, that means, it is only radiating red wavelength corresponding to red color, and still cool it, its color is nearly iron black color, right. I mean iron, normally the grey black color of the iron, but it is still hot. So, it is radiating only the heat radiation. So, you see the quality of radiation is a function of temperature, quality of radiation is a function of temperature. Now, earth we are assuming that is around 25 degrees centigrade, 288 Kelvin. So, the radiation, quality of radiation, this is long wave radiation. So, this is long wave radiation, this is long wave radiation, this has got short wave radiation, out of which there is a small portion which is visible, right, and this small portion where I have the peak again, So, this is visible range, this is visible range. Beyond that, ultraviolet and infrared heat radiations are also there, but here it is all heat radiation at 288 Kelvin, right. Now, this part shows absorptions by methane, because earth radiates in the nocturnal sky when sun is not there, radiation heat exchange will be between the earth and outer cosmos, right, and the methane absorbs most of this radiation, right, at this level, this is the peak, as you can see there. Then if you look at nitrous oxide, it is somewhere here, oxygen somewhere there, carbon dioxide, you see it has got quite a bit of big spectrum, good lot of it absorbs here, and this is also absorbed, and this is also absorbed, and this is also it absorbs this. So, it is a bigger spectrum, and water vapor. So, these are the greenhouse gases, So, these are greenhouse gases, right. So, they absorb, that is what they absorb actually most of this. Now, if you see, this is absorptivity, these values are absorptivity, right. So, this is why these are the greenhouse gases which absorbs quite a bit of them, and atmospheric window through which actually it goes out, these are the absorptions, majority of it gets absorbed by the earth and so on, this is the visible portion and so on. So, that is why now you get a better idea of what is greenhouse, why they are greenhouse gases and the spectrum in which they actually absorb. Now, of course, earth energy balance, I think I might have talked to you sometime earlier or may not have, but whatever is received by earth, in a year it must go out, whatever is received by earth in a year should go out. Actually 50% of it goes away straight from the, so if there is a top of atmosphere, 50% of it does not reach the surface, and I think I might have mentioned this earlier, this 50% over the year also goes out, some by evaporation, some by radiation, some by convection to the upper layer and those. So, heat balance of the earth is like that, right. But then absorption see focused by those ones, then they will trap it. Okay. So, but we are not today, we are not talking much about that. So, let us say now this is, if we take any surface, if it is transparent, it will transmit some, they are all fractions, reflect some and absorb some. So, at a given wavelength, any body, transmission, absorption and reflection, they are fractions, because absorptivity is defined as the fraction of energy absorbed divided by total energy incident upon it. Reflectivity is defined in the same manner, fraction of energy reflected back, right, divided by energy incident, and this is transmitted. So, a transparent body of course will transmit. So, this is the sum total. So, this is absorptivity, this is transmittivity and this is reflectivity. For opaque surface tau is 0. For opaque surface no transmission would occur, reflection can also be okay. So, this is what it is. Now, this what we call as specular reflection, angle of incident theta incident theta r, these are same, this is related to specular reflection, this is related to specular reflection, but if it is diffuse reflection it will go in all direction. So, reflection can also be diffused, reflection can also be diffused, right, reflection can also be diffused actually. Okay. So, 1 minus, if it is an opaque body this would be 0, this term would be 0, then this two sum must be equals to 1. So, 1 minus this is equals to 1 minus absorption must be equals to 1 minus absorptivity must be equals to reflectivity. We will use them later on, So, this is what it is, whatever is coming in a body, part of it is reflected, part of it is absorbed, right, part of it is absorbed, and this is the sum total. Now, aerosol in the atmosphere, they are fine particles suspended in the air. Air can have colloidal solution. So, this solutions, colloidal solution means what? Particles are of sufficiently small size, and if it is a uniform solution you pick up from one portion, pick up from another portion, you will find concentrations are similar, right, if it is a uniform solution. Suspensions are larger sizes, or colloidal solutions are larger sizes. So, they are not exactly, you might find in a colloidal suspension concentration is more of solids, let us say in water, soil and water, you make a turbid solution, you find more particles at the lower level than at the higher level. So, that try to settle. So, in air also same thing can happen, particle can remain as suspension. So, if you look at diameter in microns, the equivalent Ettinger nuclei as they call it name, right. So, 10 to the power minus 3 micron, these are in microns, to 10 to the power 3 microns, which means 1 millimeter. So, we are looking at these sizes. So, this is clouds, then various combustion sources, particles, secondary sources, gas particle, photochemical reactions, cloud droplet, etc., and there we have got settling velocity. So, particle size smaller than 2.5 micron, 10 micron, and their settling time, if you see, less than an hour, and some which are large particle, they can take longer time to, much longer time, to days and weeks and hours to settle. So, therefore, radiation absorption is also there, this one absorbs the radiation. For example, this range ultraviolet radiations are absorbed, in this range far infrared radiations are absorbed, visible to near infrared, they are absorbed in, these particles absorb this. So, particle also absorb this the aerosol particle absorb this, right, and they transmit them, some to the outer cosmos and some to the ground, right. So, that is what it is. So, they interact. Now, just to recollect, some of you might have already done a course earlier building science or somewhere, you might have come across little bit of radiation issues. Supposing, but then here you will be using this here as well as later on also maybe. So, we go define certain angles. Now, these angles are, first of all, this is altitude angle, this is altitude angle of the sun. So, if I have the surface, this is normal to the surface, sun's radiation, sun is somewhere here, sun is somewhere here, sun's radiation comes into the surface, this angle we call it solar altitude angle, that is normal to the surface, the angle the sun's ray make with the normal to the surface, this we call as altitude angle, right, and altitude angle. So, solar altitude angle normal, this is the projection, this is the normal to the surface, is projection to the horizontal plane is this. So, altitude angle is the angle between sun ray and projection of the normal to the surface on horizontal surface, So, that is altitude angle, right, and this is called, we call incident angle. Incident angle is the angle between normal to the surface and sun ray, right, normal to the surface and sun ray. Now, sun's position is defined by two angles, one is this altitude angle, another is azimuth angle. Azimuth angle, one convention and more commonly used convention is this, take geographical north, and this is the this is the sun's rays projection onto the horizontal plane, this angle we call as solar azimuth, this angle we call as solar azimuth. So, in the this is the north direction, this is the north direction as shown here, south, east, west and all that, right. So, this is the azimuth, solar azimuth. Solar azimuth angle is the angle made in the horizontal plane from a reference line to the projection of the sun ray onto the on that plane. So, this is diagrammatically these are like this, and if I write them out. So, azimuth angle is angle between sun ray projected on horizontal surface with a reference point usually from north measured clockwise. So, now from north measured clockwise, So, this is the horizontal surface, this is the horizontal surface, this is the horizontal surface, this is in the horizontal surface, this is the north direction. So, from here to this we call as solar azimuth angle, right. So, measured clockwise. Then altitude angle, angle between sun's ray and its projection on horizontal surface, angle between sun's ray and projection. So, this is the projection of the sun ray onto the horizontal surface and this is the sun ray. So, this is your altitude angle. Okay, there are some more angles, although I may not be using them. Surface azimuth, if you want to measure the surface azimuth, which I may not require here, but these angles I just thought that let them be their definition. Supposing this is the normal to the surface, if I project it onto the ground, I will get some line, some line somewhere there. If I project this line, this is the projection of the sun ray here, projection of this line here. So, this angle I will call as surface azimuth, azimuth of the surface, normal to the surface projected onto the horizontal plane, angle between that and the north direction measured clockwise, we call it surface azimuth, or in case of a wall I will call it wall azimuth. For horizontal surface, obviously this angle is not really relevant, because normal to the, it will be normal to the surface will be vertical and its projection onto the ground will be simply a point. So, the result will be 0. Then we define incident angle, right. Incident angle is the angle between sun ray and normal to the wall or surface. So, if you see this, this is what I defined, this is what I defined, this is the angle, right, normal to the surface and sun ray, that is incident angle. So, this is incident angle, right, this is incident angle. Then we define surface solar azimuth, that is the azimuth angle between the two, right, although again it is not very important, angle between the projection of normal to the wall or surface on horizontal plane and sun ray projected on the horizontal plane. So, this we will not need it here actually, but supposing this is a projection of this line over ground. So, projection of sun ray is here, this is wall solar or surface solar azimuth. That is the azimuth difference between the azimuth of sun and the surface. Difference, projection of the normal to the surface onto the horizontal plane, projection of the sun ray onto the horizontal plane, the angle between them we call it surface azimuth. In case of wall we call it wall solar azimuth. If I am interested in finding out the radiation or incident angle for a wall or a surface, this becomes important, right, this becomes important. So, for horizontal surface simple, if I have radiation falling like this, I call it beam radiation, because I said that radiation will be, reflections could be two types, specular or diffused. Now, in case of sky world, the sun is somewhere, in case of sky world, sun is somewhere there, if this is the plane I am considering. So, I will get beam radiation like this, but radiation will also come from other places, let us say from these portions also, because atmospheric aerosol etcetera will absorb and they will diffuse, it will go in all directions. So, if the particle here, it will diffuse the solar radiation in all direction, and I will get a lot of diffused radiation from all direction here. So, I have two types of radiation, one is the beam radiation, another is diffused radiation. So, let us look at the beam radiation. So, this is the beam radiation. So, I call it IB, is coming onto this surface, is normal to the beam radiation is this, right, and this is the normal to the surface for a horizontal surface. So, this angle, altitude angle is given as, because its projection will go to the ground. So, altitude angle is given as projection of sun's radiation onto the horizontal surface and the sun ray itself, this is altitude angle. This we call, this is this is the incident angle actually, or you can write it like this for horizontal angle. So, this is 90 degree minus beta in this particular case. So, this is incident angle, or we can write it, denote this by simply this. So, IB, because IH is nothing but equals to incident angle itself here. So, IB cos I, because this is what is I and angle between these two is IH. So, the radiation falling here will be falling on larger surface, same radiation, because intensity of radiation in 1 per watt per meter square. Now, it is falling over a larger surface now. So, the radiation that is falling onto this surface will be given by cos into this angle, because this angle is same as this is normal to this and this is normal to this. So, this angle is again right. So, this surface length is horizontal surface. So, cos of incident angle. So, cos of incident angle. So, it will fall onto a larger area, therefore, intensity will be less. The intensity, if this is the area, let us say normal area. So, IB normal area AN is the total intensity coming, that must be equals to IH, and this is the area horizontal, and area horizontal by area normal by area horizontal is nothing but cos of IH, right. So, IH is equals to incident angle in this particular case. So, IB cos H, this is cosine law, simple as that. So, IH on horizontal surface it will be, or in this particular case it will be sin beta, because this is 90 degree minus beta. So, IB sin beta. So, on horizontal surface for any other surface it will be given as, in this case of course, it is like this, for any other surface it will be given as IB cos of incident angle, IB cos of. So, I on any angle would be given as IB cos of incident angle, cos of incident angle. That is how we define cos incident angle, we have defined earlier like this. So, cos of incident angle for horizontal angle it is simply like that, right, horizontal surface simply like that. So, I can actually measure, or if I am measuring horizontal radiation on horizontal surface is easy, beam radiation can be calculated. Anyway, I am not really for a surface, this is what it is, I b cos, on that surface I b cos, so I h cos theta by sin beta, one can find out in this manner as well. So, this is what for any surface. So, if this was an inclined surface as we have seen earlier, this is inclined surface. So, this is whatever is the normal coming multiplied by cos is the amount of radiation that will be falling onto that inclined surface, right. It will be falling onto that inclined surface. Okay. So, that is it as far as surface radiation on surfaces are concerned. Now, total radiation received by the received on earth is direct radiation, net direct radiation and net net short wave radiation and net long wave radiation. So, the star denotes the net radiation received. Q star is the net radiation received by the earth. K stands for short wave, L stands for long wave. So, Q is net all wave, K stands for short wave, L is long wave radiation. So, this is downward what is coming in, that must be equals to beam radiation plus diffused radiation, as I mentioned, diffused radiation coming from all sides because particle will absorb, and sun is very large compared to sun's rays falls like beam onto the whole surface of the earth. This is earth is small. So, it comes from all directions. So, if this is your horizon, this is your equator plane, and at any point of time sun's radiation will come from all directions, and it's here of course on the surface, supposing I am interested on a surface here, I will get normal radiation, but I will also get radiation coming from diffused radiation coming from all this direction as well, because atmosphere will diffuse the direct radiation of the sun and to receive. So, always you have the short wave. So, if you look at short wave radiation, I beam plus I diffused, and if I look at some of it will be absorbed, some of it will be absorbed and some will go away. So, this is going up, this is going down. So, these are short wave radiations coming in, a fraction of it will go away. So, this is called albedo, this A is called albedo. Albedo denotes the fraction, right, which is the ratio between the radiation going out of the earth divided by radiation, short wave radiation incident. This is all for short wave radiation, right. I can combine for all wavelength and average we can take. Now, this would be, since K star is how much, is the net. So, it is difference between these two. K star was net, K star was net, which is K downward minus K upward, and this is nothing but K downward. So, this is K upward is equals to K downward minus A K downward. So, therefore, I can write it like this. So, net is 1 minus albedo K downward, what is received by the earth. So, right, what is received by the earth. Long wave radiation, we have said that epsilon at given wavelength must be equals to absorptivity at same wavelength, right, absorptivity at the same wavelength. Therefore, reflectivity, since earth we are assuming it is opaque. So, whatever long wave radiation comes into it, nothing will pass through it, it will be reflected back, right, and that would be 1 minus absorptivity, 1 minus absorptivity, and absorptivity is same as emissivity. So, I can write as 1 minus emissivity. So, reflectivity is nothing but 1 minus emissivity for a given wavelength, because we are saying absorptivity and emissivity is same, and there is tau is equals to 0, since tau is equals to 0, tau is equals to 0. So, this can be, so reflectivity is nothing but 1 minus emissivity. So, part of the radiation emitted and part of course reflected, part is emitted, part is reflected. So, we can write this the long wave radiation which is going out, part is radiated back, part is reflected, and we have seen reflectivity is nothing but 1 minus this. So, this is the long wave emissivity, whatever is coming in 1 minus that will be reflected back. So, this is the component reflected back, this is the component reflected back, and this is the component going out by radiation. This is the equivalent earth temperature. We assume the cosmos is at negligibly small temperature or absolute 0 temperature or whatever it is. So, therefore, T to the power 0, that is the amount of heat that would go out, right. So, this is epsilon, and this seeing everything on the cosmos, I mean totally. So, on an average basis one can think in terms of this. So, therefore, the two things, one, albedo relates to short wave radiations and emissivity of long wave radiation is important, because 1 minus emissivity is again the reflectivity, 1 minus emissivity is again the reflectivity, right. So, if you see bare ground, its albedo is somewhere there 0.505 to 0.3, it would vary depending upon whether it is a desert or just soil, rocky area. So, we are looking at bare ground, no vegetation. So, this will vary. A desert actually has got a higher value of albedo, right, because it reflects more, surfaces are, it will absorb less, a soil will, some of the other soil it might absorb more. Vegetation, this is the value, right, and forests, water, urban roads, snow gives away most of it, right. Snow gives away because it is white, so it will reflect, it will radiate everything. And concrete, which is relevant for us, 0.1 to 0.35, CGI sheet can go something like this. So, there varies, actually there are ranges, I have just picked up a small portion of it. And glass, it will also depend upon angle of incidence, so is water. It depends upon angle of incidence. At 90 degree, of course, it reflects maximum, lesser angle it will reflect relatively less. So, albedo values varies accordingly. Urban and rural, plants and paints and metals, even up to 0.9. So, albedo values varies depending upon type of surface on the earth. And if you see long wave emissivity, which is important, that was for short wave, this is for long wave. So, bare ground 0.89 to 0.98. So, it emits good lot, it emits good lot, vegetation something like this, forest something like this, water, most of it is actually emitted back, concrete, but some of the surfaces can be lower, and glass, urban area, rural and so on. So, that is what the albedos are, emissivities are. So, emissivities are usually higher, order of 0.8, 0.9 etc. for most of the surface, and albedo of course varies depending upon surface. Snow would have much higher value. So, that is what is related to absorption by the earth.